OpenStack Physics, Chapter 6, problem number 19. The problem gives a little preamble, which is nice, about how to make artificial gravity. So we can indeed make artificial gravity, and it's with a rotating spaceship. So you see this in a lot of science fiction movies. They're like, hey, let's have the spaceship rotate, and that'll cause artificial gravity, and that's true. It would totally work. And then you can film it on Earth and make it pretend like you're in the spaceship, and then there'd be gravity. You don't have to worry about things like that. So it's actually a good idea. It totally would work. Okay, so how does it work and why does it work? Let's talk about that really quick. So if you remember, if I have an elevator and I'm standing in the elevator like that, and the elevator is at rest, then the gravitational force pulling down, mg, and the normal force pushing up would be equal, and you would feel fine. You feel normal. Now, if the elevator accelerates upwards that way, well, what forces are acting on you? You still have the gravitational force, but it doesn't change if you're near the surface of the Earth. But you have to have a net force pushing up. And so the only way for that to happen is for the normal force to push more on you like that. That's what happens. And if you've ever been in an elevator and you push that up button, you accelerate up, you feel heavier. Right? You feel heavier. And so we actually don't feel the gravitational force. We feel the normal force. So if we can get the normal force to 0, then you would feel weightless. So the same thing happens when the elevator is moving up and it's slowing down. Now you're accelerating down. You're accelerating. And so the only way to do that is to have a smaller normal force. And so when you get to the highest point of your trip in the elevator and start slowing down, you feel a little bit lighter because the normal force gets smaller. Gravity didn't get smaller. If you accelerate down at 9.8 meters per second squared, then the normal force would be 0 and you would feel weightless. And that would be bad because it means the elevator is falling and something bad is going to happen. But let's hope that doesn't happen. There is that amusement park ride, the Tower of Terror, and it does that. It drops the elevator down, but then it like curves and slows down, doesn't just crash into the ground, which would be bad. Okay. So, but the point is that if I make the normal force equal to mg, then I would feel like I have mass. And I'm going to tell you another way after this rotating spaceship thing, another way. If you're a science fiction fan, I'm going to tell you another way to make artificial gravity that's in a show that I like a lot and relates about what I like. So let's go back to my rotating spaceship. So, and you see this in 2001: A Space Odyssey, The Martian, Babylon 5, Elysium. I'm thinking of all the rotating spaceships they have out there. There's a bunch. And this is how it works. 2010, A Space Odyssey. Okay, so let me redraw my picture right here. I have my space. That's a terrible circle. I can do much better than that. My circle, that's not bad. And let's draw my person right here, standing on the inside of the space station, and the space station rotates around this way. What movie was I just watching? Oh, what was the movie? The show. For All Mankind. Rotating space station too. So we want to say I want the normal force to be equal to the equivalent of being on the surface of the Earth. I have the radius of the space station is 100 meters. It said diameter was 200, so that'd be radius of 100. And we're going to find that. So let's draw how the forces on this person. I have the normal force pushing this way. Now, so we're going to assume that we're in space, in deep space. Technically, you could be in orbit, and this would still work. But there is a gravitational force, but the problem is the space station's accelerating too, so it's as though the gravitational force wasn't there. So let's just pretend like it's in deep space. There's no masses or anything like that. That's the only force acting on it. So let's call that the x direction. I always do this. I don't know why I put my person right here, and so the force is in the negative x direction, but it doesn't matter. I can write F net x is going to be equal to negative n. The normal force is in the negative x direction, and that's going to be negative m omega squared r. Right? So this is the mass times acceleration, and the acceleration is v squared over r, or the angular velocity squared times r. You can write it either way. And in this case, I want N to be equal to mg. So I'm going to say mg, now the negatives cancel, equals m omega squared r. And now I just have to solve for omega. That's it. Okay. So the mass cancels, which is really cool because different people will have the same effective weight because they'll have a more normal force, but they'll feel the same way. And I can solve for omega. So omega is going to be the square root of g over r. Let's put in our value. Square root of 9.8 divided by 100, which is the square. Well, I'll just put in my calculator. Where'd my calculator go? Here it is. Found it. Sorry. Okay. On. Drop. 9.8. Enter. 100 divided by square root. I get 0.31. 0.31 radians per second. Okay. That's how fast you have to rotate. Not too bad. Let's just convert that to RPM just because I think it'd be useful. So omega is 0.31 radians per second. And so I'm going to convert the radians first. So to convert radians, I can say 1 revolution is 2 pi radians. And the radians cancel, even though the radians aren't even really a unit anyway. And then I want to convert seconds to minutes. So I'm going to say there are 60 seconds in 1 minute. And the seconds cancel. So if I take that value, multiply by 60, divided by 2 pi, so 60 times 2 divided by 3.1415 divided by, I get 2.98. 2.98 RPM, which is actually kind of fast, but that's what you'd have to do if you want full gravity. So how could you make it rotate slower? Well, there's two things that you can do. Number one, you could not have G. What if I only want half a G, right? Half a G is better than no G at all. So I could do that. Or two, I could make R larger. A larger space station doesn't have to rotate as fast. A smaller space station has to rotate very fast. Now, there's another interesting thing. Imagine that I have a very small space station. 100 meters is not that. That's pretty big. But let's say it's like 10 meters. So my person would be like this. I'm going to just draw a bigger person. If I do that, then what's going to happen is that my head is moving in a circular orbit, a circular radius that's much smaller than my feet. So the gravitation, the effective gravity at my head and my feet is not the same. So, but the bigger the spaceship is, then the difference in radius for your head and your feet is very small. If I have a 100-meter radius, then my head will be at about 98 meters. My feet will be at 100 meters. Not that big of a gravitational force difference. Okay. Now, I did tell you I was going to tell you another way to make artificial gravity, and this does show up in at least one show. I'm trying to think of another one. If you like science fiction, watch this show. The Expanse. I like it. So in The Expanse, they come up with a way to make rockets that can essentially have endless thrust. And so if you can have endless thrust, you can take a rocket. Here's my rocket, a terrible rocket with rocket nozzles right over here. And I can stand like that. So if the rocket is accelerating this way, then the forces on me, I'd have a normal force pushing me that way. So I could create a normal force by standing on an accelerating rocket ship and just accelerating. And so then if I want to stop, what I do is I just turn the rocket ship around and again turn on my thrusters and accelerate this way. But as long as my feet are pointing towards the thrusters, I'd feel gravity. I'd feel effective weight. And that's what they do in The Expanse. And I think they do a pretty good job of it. And it really helps with the filming because then you can film in a studio instead of having to be in real space. And then when they have space scenes, they use magnetic boots sometimes. But I should point out also that the movie Apollo 13, what they did was to take the studio of the Apollo spacecraft with Tom Hanks and who was I know the guy in my head Kevin Bacon, and then the other guy in there, and they put that studio inside of a plane, and then they took that plane and then they flew in a parabola, and during that time the acceleration was negative 9.8. So the people inside looked weightless, and it made a great visual effect because it was weightless. It was no different than being in space. But the problem is you can only do that in short time intervals because you can only do this for 30 seconds to a minute, and then you got to pull back up. So you can only do that like that. But it looks great. Apollo 13, great movie. Not even science fiction. Okay, there you go. We could talk about science fiction all day, and we should probably just stop. So.